Temperature and Time Influence on the Strengthening of Medium and High Carbon Steels by Delton Friedman. Introduction to Engineering Alloys, or MECE 5339 is the class that this paper was for. The goal of the paper was to explore the effects of heat treatment on the microstructure of medium and high carbon steels and the effects that those microstructural changes have on the mechanical properties of steel. The summary of the work. An exploration of how manipulation of temperature for differing durations can affect the phases present as well as the ultimate morphology of those phases. Resistance to deformation as a function of the distribution of carbides was explored, as well as how to affect that distribution through means such as control of prior austenite grain boundaries and others. It has been well known, at least qualitatively, for quite some time now that finer distributions of cementite are stronger than coarser ones. This distribution can be controlled through a variety of heat treatments, but in general, larger undercooling will lead to a finer distribution of particles. Through their research, Gensimer et al. Has established a relationship in which the resistance to deformation of a metallic aggregate consisting of a hard phase dispersed in a softer one is proportional to the logarithm of the mean straight path through the continuous phase. They have therefore been able to quantitatively define what has been known qualitatively for quite some time. The figure to the right shows the properties of steel of a few different carbon concentrations as a function of the log mean ferrite path, which is a well-defined quantity in the work of Gensimer et al. In the figure, the top group of points is the tensile strength, the middle group is the yield strength, and the bottom group is the hardness. It is apparent from the figure that there is a definite correlation between the log mean ferrite path and the properties represented. There are a number of different methods for controlling the distribution of precipitates. One of the strategies we discussed in class was the degree of undercooling, which works because of the change in diffusivity as a function of temperature, as well as the dependence on the critical radius on temperature. Another way to control the distribution of cementite is by controlling the size of the prior austenite grains. The figure to the right shows two stress strain curves for a couple of different prior austenite grain sizes. The various curves represent martensite tempered at various temperatures. As can be noted, there is a slight improvement in ductility based on those which were quenched from smaller prior austenite grains,